You ever see one of those massive cargo ships and just stop and think, how on earth is that thing not at the bottom of the ocean? I mean, it's just a mountain of metal. Well, let's get into it because the answer is actually way simpler and frankly, more beautiful than you'd expect.
Yeah, this is the classic head-scratcher, isn't it? You've got this 100,000-ton steel ship just casually floating along, and yet you take one little coin, flick it into the water, and boom, sinks like a stone. It feels like it just shouldn't work that way, right? Like it completely defies logic.
But you know what? It's not a paradox. Not at all. There is one single, really powerful concept in physics that unlocks this entire mystery. It explains why some things float and others sink, no matter how big or heavy they are.
And that one big idea is density. Yep, that's it. This one word is the key that explains the ship, the coin, and honestly, a ton of other things you see every single day.
So, okay, what does that even mean, density? Well, the easiest way to think about it is packedness. It's just a way to measure how tightly all the little bits of matter, all the stuff, are crammed together inside something.
And to really get a grip on this idea of packedness, we have to break it down into its two key ingredients. It really is all about mass versus volume.
All right, so let's break this down. Mass is basically just how much stuff is in an object, the actual matter. And volume, that's just how much space all that stuff takes up. The classic example is perfect here. Think about a pound of feathers versus a pound of lead. Same mass, right? 1 pound. But the feathers take up a huge amount of space. That's high volume. The lead is tiny. That's low volume. And that difference is, well, it's everything.
And this all comes together in a really simple formula. You just take the mass of an object, all that stuff, and you divide it by its volume, the amount of space it takes up. That's it. So if you cram a lot of mass into a tiny volume, you get something that's super dense. But if you have just a little bit of mass spread out over a huge volume, not so dense at all.
Okay, theory's one thing, but let's make this real. How would we actually figure out the density of that coin that sank? Let's get practical and measure its packedness.
Turns out, it's a pretty straightforward two-step process. Step 1, you find its mass. Easy enough, right? You just pop it on a scale. But step 2, finding its volume, that's a bit trickier. I mean, you can't exactly measure a coin with a ruler. For that, we need to use a really clever method.
And this is it, the water displacement method. So check this out. We start with the water level at, say, 42 milliliters. Then we drop our coin in. Plunk. And you see that? The water level rises. Now it's at 52 milliliters. That jump is exactly what we need to know. So why did the water level go up? Well, the coin had to push some water aside to make room for itself, right? And the amount of space it took up, the volume of the displaced water, is exactly equal to the volume of the coin itself. So we do some simple math. 52 milliliters minus the original 42 gives us 10 milliliters. And that, my friends, is our coin's volume.
Okay, now we have both pieces of the puzzle. Let's say we weighed the coin and its mass was 50 grams. We just plug our numbers back into that formula. 50 grams divided by 10 cubic centimeters. And voila! We get a density of 5 grams per cubic centimeter. We've cracked it!
All right, so now that we know how to calculate density, we've basically got a new tool for understanding the world. Let's use it to solve some of those everyday puzzles.
And that brings us right back to the beginning. The big question, how is that giant steel ship floating when our much smaller, denser coin just sank? The key here is that it's not just about what the ship is made of, it's about its shape. If you took all that steel and squished it into a solid block, oh yeah, it would sink in a second, because steel is way denser than water. But a ship is mostly empty space. It's a cleverly designed hull filled with a huge amount of air. And when you calculate the density of the whole thing, the steel and all that air combined, you get its average density. And because of all that air, the ship's average density is actually less than the water's. That's the whole trick. If its average density is less than water, it floats. A submarine is like the ultimate example of this principle in action. They are masters of changing their average density. When they want to dive, they open up tanks and let water flood in. This makes the sub heavier, increases its average density, and down it goes. And when they want to come back up, they use compressed air to blast all that water out, making the sub lighter, lowering its average density, and it rises right back to the surface.
All right, here's another puzzle for you. Have you ever been swimming in the ocean and noticed that it feels, well, easier to float than in a swimming pool or a lake?
Yep, you guessed it. It's density again. All that dissolved salt in the ocean makes seawater denser than freshwater.
And since you're floating in a denser liquid, that liquid is pushing up on you with more force. It's just plain easier for your body to float.
And speaking of things floating in the ocean, let's talk about icebergs. We all know they're incredibly dangerous for ships, but why? What is it about them that's so sneaky?
Well, the danger is exactly what you can't see. See, ice is less dense than water, that's why it floats. But it's only a little less dense, and because of that small difference, the vast majority of it, about 90%, is lurking hidden beneath the waves. That tiny little peak you see sticking out of the water is hiding an absolutely gigantic mountain of ice just below the surface.
And the whole fact that ice floats at all brings us to one of water's weirdest and most amazing secrets. When it comes to density, water is a total rebel. It breaks a major rule of physics.
And it all comes down to a magic number, 4 degrees Celsius. This is the point where water starts to do something completely bizarre.
Okay, so for pretty much every other substance out there, the colder it gets, the denser it gets. The molecules huddle closer together. And water does that too, but only for a while. It gets denser and denser as it cools until it hits 4 degrees Celsius. Then, from 4 degrees down to freezing, it does the exact opposite. It starts to expand, becoming less dense. This wild property is why ice floats. Without it, ice would sink, and our lakes and oceans would freeze solid from the bottom up.
So there you have it. From a massive steel ship to a floating ice cube, it all comes down to density. Next time you see salad dressing separate or watch a hot air balloon drift into the sky, you'll know what's really happening. You've got the key. So the only question left is, what else in your world can you explain with it?